Okay, so last time when we were working on the curve fitting problem, we took a step towards the Bayesian approach by bringing in a probabilistic perspective. So remember initially that we had some data from a particular curve and we were trying to fit it to some polynomial function, and we sort of in an ad hoc but kind of reasonable way said, well, why don't we try to have kind of a goodness of fit function, kind of an error function that measures the the kind of the average energy, the average squared deviation of our predictions from each of our data points. And we have some parameters and we modify that. And we found that that did okay, but when we made the polynomial very complicated, then we start getting very wildly fluctuating fits that went through our data points, but seemed like they were too complicated for the data that for the data generating process that we knew we had generated our data from. So then we brought in this idea of regularization to kind of maybe keep our weights small, because we noticed that those fluctuations were due to very large contributions from the different polynomial components canceling each other out. So we said, okay, well, maybe it makes sense to regularize our weights to try to penalize them if they get too large, and that improved the problem, and we got better looking fits. But that procedure was a little bit ad hoc. So what we did in the last section was we said, okay, well, let's think of our data as coming from some probability distribution. So our data are normally distributed around some mean value that depends on the data point, and with some fixed variance. And we saw that with just that step, the energy function that we got out and the regularization that we got out as functions of our weights suddenly emerged, and they had these really nice probabilistic interpretations. So now, instead of saying, well, this energy function is kind of reasonable, and this regularization is kind of reasonable, but then not, why is it reasonable? How would you improve it? Well, now the probabilistic interpretation gave us a way of thinking about the energy function as being the log likelihood under a normal model of the data points, and the regularization being due to a prior on the weights, particular prior on the weights. So that was a great first step, because now we can actually talk about these things and talk about ways of how we can improve them, and how we can if people disagree about aspects of the model, we can talk about concretely, rather than trying to come up with ad hoc improvements, or argue kind of more vaguely that way. But nevertheless, at the end of that chapter, we were still kind of dealing with point estimates. So we had this nice interpretation of our energy functions and a regularizer, but we were still using them to produce, let's say, a maximum a posteriori post estimate of the weights. And so now we're going to go kind of the full Bayesian way, not about the weights, in fact, but about our predictions. So we're going to see how by just applying the rules of probability, we can come up with a really nice and kind of principled. What's nice about it is that principled distributions on new data points, and how we can do that, and how it's really quite straightforward. So there aren't mysterious steps. So that's kind of the Bayesian, the full Bayesian aspect, using the rules of probability to go from prior distributions to posterior distributions, not point estimates. Okay, so let's get going. So the chapter is the Bayesian curve fitting, which is what we're going to be talking about. So yeah, as he said, we've brought in the prior distribution on weights last time, but we're still making point estimates. So remember that we probably weren't necessarily interested in those weight vectors themselves. We're interested in making predictions. So the whole idea of of this section is how we can do that by integrating over all the values of W. So this is a very crucial operation that is done all the time. It's called marginalization, and it's really it's absolutely crucial, and we're going to see an example of it here. Okay, so let's continue. So in this problem, we have our training data x and t, and again, we don't care about the values of the targets on our training data. We already have those. We want to be given a new test point and to predict the value of t. So you've got some training data, and now you want to use that training data to predict the value of your data on a new test point. So what we're really interested in, the quantity that we really care about, is this predictive distribution. So it's the probability of t, the target value, given the new value and all of your history. So all of the training data you've been given. And for kind of the sake of clarity, we're going to drop these hyperparameters that we had. So remember, alpha was our prior on the weights, related to the prior on the weights, and beta was related to the likelihood term. So we're just going to assume that these are fixed in advance, just to kind of avoid clutter here. But later on, we'll talk about how you would learn these as well in future sections. Okay, so the first idea is, well, how do we come up with this distribution? And he's kind of written it as this particular formula, and indeed you come up with this by just applying the sum rules of probability, sum and product rules. But I think there's a little bit more going on here than meets the eye. I'm sure we'll talk about this in detail in future chapters, but I thought it's worthwhile looking into exactly how this expression comes about from the sum and product rules. So let's just I'm going to go and let's just talk about that here. So we've got, I've just written this up, so we'll just go through the calculation. It's very brief. So here is the expression that we want. So here we want the target value conditioned on our new value and our history of training examples. So these are the inputs and the outputs. So how do we do that? And well, so you need to kind of have a framework for how you're approaching the problem. And our framework here is we're going to say, well, these target values are related to the inputs through this this function of the polynomial function of the inputs, weighted by this vector w. So let's do that. So we're going to say there's going to be some parameter w, the weights in our case, and so now we're going to apply the sum rule of probability or marginalization to express the left-hand side, so this marginal probability, sorry, this posterior probability on the new target in terms of those weights. So let's just do that. So that's going to be, we're going to integrate the target, so the joint distribution of the target and the weight vector, given our new input, our history of inputs, and our history of targets. Okay, and this is like a general statement, so you don't even have to know how t and w relate. But for any variable, this is like a probabilistic identity. Okay, so now the question is, how do we go further with this? So, and that's where the product rule comes in. So again, we're not doing anything. We're just saying, look, there's some variable w that we care about. Now you'll remember that there was a joint probability of A and B. Remember, we could think about this as the probability of, let's say, A happening times the probability of B happening given that A's happened. Right? So that was the product rule. So we're just going to apply that here, but we're going to be applying to these conditional probabilities. And all that does is you just have to remember to keep these things you're conditioning on the right side of that bar. But that's about it. So let's erase this and let's write out, let's apply the product rule here. So this is going to be equal to t given w x x t times pw given x x t, and all of this dw. So we've done the sum rule, and now we've done the product rule. And again, this is perfectly general. So if you tell me there's some variable w you care about, I don't need to know anything about its form to be able to write this decomposition here. But it's at this point where now your conception of the problem comes in, because you need to now somehow simplify this into a kind of a tractable way, or into a way that reflects your understanding of the problem and your knowledge. So what we're going to do, and what we've kind of done already earlier in the chapter, is we're going to actually simplify these two components based on our knowledge of the dependencies that occur in the problem. So one of the key assumptions, and these are both assumptions that you might make because the problem then becomes tractable, or because you just know that's how the particular problem works. So it's about using these conditional dependencies and independencies. So what we're going to assume is that the probability of a target given the weights at a new point. So we're going to assume that if you know the weight, so if someone's giving you the weight, then the probability, that's all the information you need to determine the target value at a new data point. So another way of saying that is that once you know what the weight vector is, you don't need to know what the training examples were to give the distribution on a new data point. So all of our information that's contained in the training vectors have now been compressed into the weight vector, and that's a really powerful idea, and that's kind of going to be the key to making a lot of these computations we're going to see tractable. Just exploiting the fact that all this information, all these inputs and outputs have now been compressed into a particular variable of your model. So we're going to write this as, so this is a simplification, which is us applying our knowledge about the model, or us expressing our assumption. And again, what's great about this is that someone can come and say, well, actually, no, I think, this weight vector doesn't contain all the information. There are some other factors you need to take into account, and then you can do that. You can extend your model to address that criticism. But now we're going to just stick with our simple model, and we're going to say that the probability, this large conditional probability, is actually can be simplified to just the weights and x. So that's the new data point, the new input, the weights, and the target point that you're predicting. So you can kind of get rid of, you don't have the dependence on x prime, the history of inputs and targets. So that's the first part. And now the second part is, well, how do the weights depend on the new target value, the new input value, and your history? Well, that one's a bit easier. We can say, well, the weights have been trained on the training data, so they don't depend on what the new input is. So we're just going to say, well, this is just P of W given X and T. So now our big integral, which is perfectly general, now we've implemented our assumptions. We've expressed our assumptions about data or our knowledge of the data, and now we have a much simpler, hopefully, integral to deal with. So now this has just become this times P, the probability, the posterior probability on the weights, given X and T, and now that is the expression that we have in the text. So I just wanted to run you through that because there's a couple of steps that we're going to see again and again, I'm sure, but I thought it would be worthwhile to go through them now. So let me switch to the laser pointer here. So this was the sum rule of probability, perfectly general. Forget it being called W. You could put in, foo bar as your variable, and it would apply exactly the same way. And then this was a product rule, and again, perfectly general. So we haven't done anything. We're just doing probabilistic manipulations. It was at this stage that now we brought in our knowledge about the problem and our knowledge of the dependencies and independencies that we use to simplify these expressions into ones that are much more tractable. And so then we ended up with this much simpler expression, which is now what we're going to talk about. Great. So let's go back up. So here we are. It's actually this guy up here. So there's the expression that we've just derived. And again, just keeping in mind that here we're just going to assume alpha and beta are fixed, and we know that they're known in advance. And just to kind of avoid the clutter, but we'll talk about how one would learn those in the future. And indeed, so what he's going to just mention next is that because of the particular form of our problem, this probability, this on W, and the probability on T, they're both going to be normally distributed, which means this whole thing is going to be normally distributed. And that's a really nice property of Gaussian distributions that we're going to talk about in the next chapter. That you actually, most of the time with realistic distributions, you're not going to be able to come up with analytic expressions, but with the Gaussian distribution you can, and it makes life a lot easier. You can actually write formulas for what the answer could be, and when you do that, you'll find that the distribution on the target values is normally distributed with a mean that depends on the input value. Thankfully, we will expect that to be the case, but also the variance now depends on the particular input value that you're using. So before we had the mean depending, but the variance was fixed. The variance was fixed at 1 over that maximum likelihood estimate of the precision. But now we see that the variance now also depends on x, the inputs. So just like so, in addition to the mean. So let's just look at this for a moment. So we've got the mean expression here. It's related to these feature vectors. These feature vectors are just the polynomial, so we can write one out actually. So feature vector for x would just be 1 x squared x cubed all the way to x to the m. So that's just what phi is. It turns out that for this problem, we're not going to go into the mechanics of it now because we're going to be talking about this in great detail in future chapters. But it turns out that that's the feature vector that you need to use. And it depends on the data points, and it depends on your history of data points. And the variance also, as I just mentioned, has this component that we'd seen before when we were just doing those point estimates, but now there's an additional component that now depends on what looks to be this covariance here. So this is a covariance, so this must be a precision. I'm not really, so one aspect that I'm not sure about is that I think this should actually be x of n, because notice that s minus 1 doesn't depend on x. And so I think this is actually x of n. This could be a typo here. But anyway, that's kind of beside the point now. I'm sure we'll see this again. So yeah, the main point is the mean, but now also the variance depend on the position. Very good. And so this contribution that we're getting now, this one up here, is actually what's being introduced by the integration over the weight. So we already had this bit before when we weren't doing any integration, we were just doing point estimates, but now we have this additional component that is being introduced because we're doing integration over the weights. So let's have a look at, we just kind of wrap this up by looking at what this looks like. So let's scroll past this and let's zoom in here. So, okay, great. So here is what it looks like. So you'll recall that this green curve, that was what the data was actually generated from, so it was noise around this point. And now we've got this is our mean estimate of the data. But now we've also got variances. So these are the variances evaluated at every single point. And it's a bit hard to see, but the variances in principle should depend on position. So I think, for example, over here, the variance seems like it's a little bit smaller than it is over there. So that's what the Bayesian approach, by integrating over our uncertainty weights, has provided us with the variance now that depends on position. I also just wanted to compare, to go back and compare these results to what we had earlier in the chapter. So you remember that when we were just using that energy function, the energy function, there was no regularization in it. So if you gave it a ninth order polynomial, just like the one we have here, so we're using an m equals 9 polynomial in this example as well. But you saw that when we didn't use any regularization before, we got this crazy wiggling curve, because you could fit the data perfectly with an order 9 polynomial, but it just had these crazy fluctuations in it, which we thought were unreasonable. So what we tried to do to fix that was to introduce a regularization on the weights. So try to keep the weights small, and then we got a more reasonable curve there. So that fits the data better. The mean looks closer to what we know to be the true value. But there we didn't have any sense of uncertainty, right? So like, how confident are we in these mean values? Are the error bars like this, or are they much tighter? We don't know. So there we had a point estimate, and we just point estimate of the weights, and we use that to produce a mean. And just for comparison, the regularization parameter was this in logarithm minus 18. So here, notice that we've got two things. So we're using an order 9 polynomial, but partly due to the regularization we're doing, which has come about through a prior on the weights. So there's these alpha and alpha parameter, which is a prior on the weights, and the beta, which was the likelihood contribution, which was kind of the precision of the data points, and we're going to assume that's known. So we assume in this particular case that we know what the true variance is, but there is some additional uncertainty due to our uncertainty in the weights. And both of those have contributed. So now we've got a mean which looks pretty good. And for comparison, the corresponding ln of the regularization parameter would be -8. So there's actually a bit stronger regularization than we had here. So that's partially due to this the very smooth curve we're getting. But now we've also got, due to our Bayesian treatment, we also have a sense of how uncertain we are about the predictions. And so you can see that actually, the uncertainty actually is quite reasonable, because the true value seems to lie within our uncertainty band around each of our points. So that's all I wanted to talk about. So let me see if I can. There we go. So the whole point of this chapter was essentially to go through an example of the Bayesian approach of, we're again always trying to predict something, and we're going to predict it by integrating it by essentially, well, first by having a probability model that allows us to split our this distribution right as an integral over the parameters of our model, but split up in a tractable way. And then to just run that through. Hopefully, we'll have some tractable integrals. Often we don't. But at the end of this procedure, we get both a sense of the mean, which which the previous methods provide as well. But now we'll get a variance as well, which will depend on our location. And so it's kind of a principled approach to how we can take our prior information about a problem, and then just use the basic rules of probability coupled with our knowledge about a problem to come up with posterior distributions on the things we care about. And that will give us, nice curves like this. So both nice means and variances that are all kind of principally motivated. So that's all I wanted to talk about in this section. And next time we're going to talk about model selection. Thanks a lot.